Okay, so we are now going to start the next section, the Goldbach Conjecture. Goldbach, it's pronounced Goldbach as if you have a K in the end, although you have CH. Now, tonight's video does not have any result. We are not going to prove anything. There are results in this section, but we will see them in the next video. Instead, we are going to discuss about some properties of prime numbers. We already know a few of them. For example, Euclid's proof tells us that there are infinitely many primes. The proof is very beautiful. And besides that, we know a few more elementary properties. For example, if a prime number p divides the product of two integers a and b, then it has to divide at least one of them. Now you can expect that there will be many more things about prime numbers which we are yet to see, because number theory is so vast and a big chunk of it is about prime numbers. Now among these things that we will see, many are proved, but many more are unproved. And the most mysterious thing about prime numbers is their distribution on the number line. If one starts writing them down, let's write the first few. And it of course goes on and on without any end. Then by distribution we mean this. Do we know all the prime numbers, their locations on the number line? Knowing them means knowing their location. And the answer of course is no. We do not actually know all the prime numbers. See, this is the thing. We only know that there are infinitely many of them. Euclid's, we have already seen that demonstration. But if, see, by this we mean this, our inability, rather I should not say inability, but so far we have not known all the prime numbers. If we are given a prime p, then there is no function which tells us what the next prime q is in terms of p. And by next prime I of course mean the one that is greater than p and which comes first. There are infinitely many greater than p of course, but which one is the smallest? This we don't know. We don't exactly know, because had there been a function like that, then there would be nothing unsolved. Now what is the next best thing that you can do when you do not have such a function? You can study the gaps or the differences between consecutive primes. Now if we look at the differences between these first few primes, then this first difference is 1, then you get 2, again you get 2, the difference between 7 and 11 is 4, so it increases a little bit. But then again you get 2, again 4, again 2, and like that the differences go. Now the differences of course are not just 1, 2 and 4. If you go at the end of the textbook, there is a table of primes. There you will find larger differences. Now let's see what the differences are, and let's see if we can at least see something about the differences from this itself. The first difference is 1, and this appears only once. This much we can immediately see. That's because it is the difference between 2 and 3, which besides being consecutive primes are also actually consecutive integers. That is because 2 is even and 3 is odd, so they are consecutive. And this does not happen again. That's because 2 is the only even prime. So if you are looking at other consecutive primes, they are odd. So the smallest difference can be 2, not 1. And you see that appearing quite a few times. But you also have 4. And as I have just now mentioned, you will find larger differences. Now, these first few occurrences of 2 may make you think that, okay, after some stage, 2 should stop appearing. But whether it is true or not is unknown. That's because only these few examples don't give you any information. You have the difference to not just between consecutive primes of this size, but actually between really large consecutive primes. For example, look at these primes. It is known that these two quite large numbers are also prime, and you can see that they have a difference of 2 between them. So, and there of course is enough numerical evidence to suggest that this 2 keeps appearing, but the conjecture is that it appears infinitely many times. This conjecture has a name also. Now, to state this conjecture, there is a small term, twin primes. A pair of primes is called a pair of twin primes if q minus p is equal to 2. And the twin prime conjecture states that there are infinitely many such pairs of twin primes, which is equivalent to saying that this difference 2 keeps appearing infinitely many times. The numerical evidence, the author says something about how many such pairs have been found. He says that computer searches have found this many pairs of twin primes less than this large number. And only (20) pairs between this number and this number. So this gives you a guess that they become more and more scarce as you go further and further down the sequence of integers. The amount of or the number of twin prime pairs that you are going to get, that on the average become It becomes scarce. But in spite of that apparent scarcity, the numerical evidence is so overwhelming that mathematicians have come to guess that there are infinitely many. But a proof or a disproof that this conjecture is false is unknown. It is not there. People are trying, but so far I won't say there is no progress. There are progress, but the full conjecture in this form, whether there are infinitely many or there are only finitely many twin prime pairs, that is not there. That is still unknown. Now, at the time of writing the book, the author says that the largest to date means in the year 2000 is this pair of extremely large numbers. The two numbers have been given. Let me write them down. This is multiplication A dot plus or minus 1. That means this times this power of 2 plus 1, that is one number, and minus 1, that is the other number. So the difference is 2 and they are prime. Both of them are known to be prime. Now each of these two numbers is 24,099 digits long. However, larger pairs have been found, and as of 2016, this is the new pair. Okay, there is an even much larger pair that has already been found. And this number is of course much larger. Let me see if I have written it correctly. 299,686,303,4895 times the power of 2 in this case is also extremely large, 129 followed by 4 zeros. This is the, so far I know, this is the latest pair of twin primes, and in this case, each number is this many digits long. Has been found in 2016. In fact, I think Terence Tao himself is also trying to prove or trying to settle the twin prime conjecture. Okay, so this is about primes being as close as they can possibly be, twin primes. But at the same time, we can create arbitrarily long gaps between primes, between consecutive primes, by producing as many consecutive composite integers as we want. Now this can be demonstrated in general. Say you are given any positive integer n. Can you create a string of n number of consecutive integers, all of which are composite? Yes, this can be done. You just need to consider these numbers: n plus 1 factorial plus 2, n plus 1 factorial plus 3, and so on up to n plus 1 factorial plus n plus 1. Let us first see how many numbers there are in this list. You see, you have 2, 3, 4 and so on up to n plus 1. Okay, so that means there are n numbers because we are starting from 2 and the last one is n plus 1. Okay, so we do have n number of integers here. Are they consecutive? Yes, because we are going to 1 from the previous one by adding 1. Okay, so that they are all consecutive. Are they composite? That is the next question. You see, they are composite, and in fact, to make them composite, we have chosen this type of form of these numbers. The first one is divisible by 2. Why? You see, 2 of course is divisible by 2, but if you expand this n plus 1 factorial, that is if you use its definition, in that expansion, in that product also 2 will occur. So 2 divides the first one, 3 divides the second one, and like that n plus 1 divides the last one. But does that automatically make these numbers composite? No. You see, 2 of course divides 2 also. That does not make 2 composite. But 2 divides 4 or 2 divides 6. These relations make 4 and 6 composite. Why? That's because these numbers are greater than 2 itself. So this will simply being divisible by 2 does not make this composite, but the fact that this is greater than 2 makes it composite. Similarly, the fact that this is greater than 3 makes it composite because it's at the same time divisible by 3 as well. Why is it greater than 2? That's because this is positive now, and this plus 2 is automatically greater than 2. So just like that, this one is divisible by n plus 1 and still it's greater than n plus 1. Okay, and the things by which we are dividing, they themselves are greater than 1, all of them. So 2 is the non-trivial factor of this first number, 3 is that of the second, for the second number, n plus 1 for the last number. So this is a string of n consecutive composite integers. And if you look at this example, say if you take n equal to 4, say you want a string of 4 composite integers, then in this form you can find them like this: 5 factorial plus 2. 5 factorial is 120. So you get 122. So this of course is 2 times 61, which shows its compositeness. Then 123. This, if you see, is 3 times 41. Then 5 factorial plus 4 is 124, which is 4 times 31, this is also composite. And finally 5 factorial plus 5 is 125, which is 5 times 25. So 122, 123, 124, 125 are all composite, and they are 4 consecutive integers. But this of course is not the only list of 4 consecutive integers which are composite. We can in fact find much smaller numbers also forming such a list. For example, 24, 25, 26, 27. These are also consecutive and all of them are composite. Or say you can start with 32, then 33, 34, 35. This is also another list of 4 consecutive composite integers. So this is something which goes against the twin prime conjecture in a sense, right? Because this creates as large a gap as you want between consecutive primes. So because of this fact, not only are primes close, but they should also be far apart in such locations. And this gives us a gross overestimate of where twin primes can occur. That is, they will occur in places where this type of thing does not happen. Okay, they will find gaps where this is not happening, at least this is not happening. Maybe something else, some other problems are also there in their occurrence, but they will avoid these places. Now, besides this, prime gaps means gaps between consecutive primes. That itself is a is something that mathematicians think about. Let's come to that now. Not just the gap of 2, but other gaps also are topics of research. So next the author says that a gap of length 778, that is between, if n denotes the Pn denotes the nth prime, then we are talking about this. A gap of this length has been found following this enormous prime. Four two eight four 2283 925351. This is known to be a prime, and after this there is a gap of this size, and then the next prime occurs. Now suddenly, why this? No gap of this size between two smaller primes exists. That is, between primes which are less than this prime, this gap is not there. Okay, so this is the first time. That means you encounter this prime, and then you have this gap, and then the next prime. So this is the first occurrence of this gap. Between smaller consecutive primes, there are also gaps, but of smaller size. He then says the largest effectively calculated gap between two consecutive primes has length 1092 with a string of 1091 composites immediately following a prime, which I don't think there is no need to write that. It will be a large number. Okay, this is already available in the text. But there is an update on this also. What the author says is the largest gap that has been found so far. The current searches have exceeded that, of course. There is a gap of length. This is 778, right? And the author says that the largest found is of size 1092, but still larger gaps. The largest so far is of this size. Okay, between consecutive primes, this gap has been found with, these things of course cannot even be written easily. Between primes, 18,662 digits long. And it was found by P. Cami, M. Jensen and J. K. Anderson. And I think I forgot to write the date when this was found, but it is recent. And something else also I found, which finds mention when this type of results are talked about. It is called the merit of a gap. I don't know what the significance of this quantity is. Say you have a gap like this, then this number, that is the gap length divided by the natural logarithm of the smaller prime. This is called the merit of the gap. So people also try to find gaps with large merit. The word merit, of course, gives us an idea that if the merit is large, then in some sense it becomes more important. I have no idea, but this thing I have found. Computer searches have not identified gaps of every possible width up to 1092. That is, gaps of this widths have been found, but not every possible gap. Not every possible gap means, say you are given a number less than 1092. Then it's not necessary that a prime gap of that size has been found. And the smallest missing gap is of size 796. And there is a conjecture regarding this also. For any given integer 2k, there is a prime gap of width, I should not say width, but a prime gap of 2k minus 1 consecutive composites between two primes for every even integer 2k. This is also unknown. Whether this is true or not, that is unknown. And now we come to Goldbach's conjecture. So you see that just a study of gaps between consecutive primes itself is quite large. It's really large. Now Goldbach's conjecture is about something else, about primes of course, but it's not about gaps between primes or something like that, but rather the ability to express a given integer as a sum of primes. Christian Goldbach in the year 1742 wrote a letter to Leonhard Euler, the famous Euler. And in that letter he made a conjecture. He said that he guessed this, that every even integer is a sum of two numbers, two integers of course, each of which is either prime or 1. This is the original form of the conjecture, and of course there is numerical evidence to suggest that this should be true, but again we don't really know because it is unsolved, it's unproved or not disproved also. We can see the first few examples where this can be demonstrated. But there is a more general formulation of this also, which says that every even integer greater than 4 can be written as a sum of two odd prime numbers. That is also, of course, unsolved. Now, if one starts looking at the even integers, say we have to start with 2. So what the conjecture says is that 2 should be expressible as a sum of two numbers, each of which is either prime or 1. In case of 2, of course, this is the only possibility. 2 is 1 plus 1. So those two numbers that Goldbach is talking about here, each one of them in this case is 1. Then we come to 4. Now 4 can be written as a sum of two primes. That is, those two numbers in this case are prime. Both of them are the same, but at the same time you have this representation also. One of those numbers is a prime and the other one is 1. What about 6? You can write 6 as 1 plus 5. Is it possible? Yeah, of course, okay. Yeah, 3 plus 3. Then 8. 8 of course can be written as 1 plus 7. Then 3 plus 5. Anything else? 4 is not a prime. And then let us write two more. Many more are given in the text, or you may simply try to write other even integers also like this on your own. 10 can be written as 3 plus 7, and of course also as 5 plus 5. I have started writing 7 like this instead of my usual this, because someone told me that this doesn't look like 7, and I think he is right. In a sense it looks it looks incomplete. The mustache of 7 is missing. Okay, so I am practicing writing 7 like this. How else can we write 12? 2 plus 10 is not 1. Then 3 plus 9, 4 plus. Is there anything else? See, when it comes to Yeah, of course, 5 plus 7. When it comes to doing actual numerical calculation, I am a complete failure. Okay, I cannot do things numerically quickly. This is what can I say? It's an inability. It's my inability. I cannot even add two 3-digit numbers there mentally. I don't know why, but this just simply is the way it is. But anyway, the numerical evidence, of course, not just this many, but as many as people have been able to find using computers, suggest that Goldbach's conjecture is true. Now, Goldbach, of course, himself was unable to prove this conjecture, and Leonhard Euler also was unable to prove it. But Euler, at a later date, countered with his own conjecture. See, this is how it's like an intellectual war. You are as if you are challenging Euler with a conjecture. See if you can prove this. He is unable to prove it. So he then countered with his own conjecture. What Euler guessed is that every even integer greater than or equal to 6 of the form, Euler's conjecture is a little more complicated than Goldbach's. Every even integer of this form, 4n plus 2, and greater than or equal to 6, can be written as a sum of two terms, again like Goldbach's conjecture, where each term, say a plus b, okay, 4n plus 2 can be written as a plus b, where each one of them is either 1 or a prime of the form 4n plus 1. Even integers are not all of them of this form, of course. Some of them are divisible by 4 also. Here we are talking about those even integers which, when you divide by 4, give you the remainder 2. Any such that is greater than or equal to 6 is expressible in this form. This is Euler's conjecture. Well, it's not called Euler's conjecture, but it's an answer to Goldbach's conjecture. If I am unable to answer your question, then I counter with my own question. What a quarrel. Just like the twin prime conjecture, numerical evidence is overwhelming for Goldbach's. In fact, I think more than the twin prime conjecture, this one has been investigated numerically. And you can guess one thing. As the even numbers increase in size, the number of ways of writing them in the form that Goldbach mentioned also increases. Goldbach's conjecture at the time of writing this textbook was verified for all integers less than this enormous number. It's 4 times 10 to the power 14. As integers become larger and larger, the number of ways of writing them as a sum of 2 primes. Okay, after some time you find that you do not really have to rely on this 1 plus something else. You can find primes, 2 primes, such that the given integer is a sum of 2 primes. And although here we see only one way of doing that for these first few quite small even integers, but this number itself increases. More and more ways of writing a given even integer as a sum of two primes emerge. For example, for this large even integer, there are this many ways (219,400) or 219,400 ways of writing this as a sum of two prime numbers. Now, whether this increase in the number of ways of writing such an integer is an advantage or whether it's a disadvantage, I don't really know in trying to prove Goldbach's conjecture. It is unsolved, of course, as I have said just now. Now, the great G.H. Hardy, Ramanujan's mentor, acknowledged its difficulty in his address to the Mathematical Society of Copenhagen in 1921. He said that this conjecture should be at least as difficult as any unsolved problem in mathematics. It is, however, known that every even integer is the sum of 6 or fewer primes. That is known. Okay, that is proved, I think. If it's written as known, that means it's proved. Now, if Goldbach's conjecture is true, if it turns out to be true, then each odd number greater than 7 must be a sum of 3 odd primes. Suppose n is odd and n is greater than 7, and say Goldbach's conjecture is true. Then n can be written as n minus 3 plus 3, and because n is greater than 7, so n minus 3 is greater than 4, and a previous formulation of Goldbach's conjecture says that any even number greater than 4 is a sum of 2 odd primes, remember. So you can write this as a sum of 2 odd primes. Thereby you have n as a sum of 3 odd primes. One of them, of course, is 3. I don't know why suddenly this has been mentioned by the author, but that's what it is. Now, the first real progress in nearly 200 years after this conjecture was given was by Hardy himself. Hardy and his associate, I should not say associate, but his collaborator, Littlewood, J.E. Littlewood, in 1922, using something called the generalized Riemann hypothesis. They were able to show that every sufficiently large odd number is the sum of 3 odd primes. Oh, maybe this is why this was mentioned. Because now from even numbers we went to odd numbers. But by sufficiently large, so what did Hardy and Littlewood do? Based on the generalized Riemann hypothesis, which itself is not something that is known to be true. Okay, if this is taken to be true, then they proved that every sufficiently large odd positive integer is a sum of 3 primes. That's what they did. And later, means in 1937, the Russian mathematician I.M. Vinogradov was able to remove the dependence on the generalized Riemann hypothesis. So Vinogradov was able to prove that same result without using the generalized Riemann hypothesis. So that means that actually tells us that yes, there is a proof, an unconditional proof, not based on something which is itself is not known to be whether true or false. So Vinogradov showed that this happens, that there exists a positive integer n naught such that for any odd integer n greater than n naught, n can be written as a sum of 3 odd primes. However, the problem is that Vinogradov was unable to show how large n naught should be. So that tells us that this proof is an existence proof. That means he showed, or rather Hardy and Littlewood started this. All of them showed that such an n naught should exist. That I think it's in that form. Nothing else is known about n naught. But someone else named Borodkin in 1956 proved that n naught, okay, how large should n naught be? An upper bound on n naught has been given. In the form of this hopelessly large number. This bound itself was later improved, if I want to call it an improvement, to this, which still is extremely large. We cannot express how large this 3 to the power 15 itself is, but this is an improvement over that. However, do you see how large this one is? It is 1 followed by 43,000 zeros. N naught should be less than that. So if somebody, see that just you see, they have really left one gap. Do you see that? They showed that all integers greater than n naught, all odd integers greater than n naught are expressible in this way. But that leaves us the gap of all odd integers less than or equal to n naught. In that gap, because it is finite, theoretically it's possible to search using computer whether in that gap also this result is true. However, that tells you that you should know, at least know what n naught is, and the answer is you don't know. We don't know. But if we can bound n naught so that we know that after this it starts happening, that has been proved, we can then have the task of simply verifying, whether the same is true in this region. But seeing how large this thing is, this task itself would be extremely challenging. These numbers are so large that most of them exceed the capabilities of computers, even supercomputers. But still, people are working on this. So there are other things in this section also that we are going to see about prime numbers. So that we will see in the next video. And that's just it for tonight. Tomorrow again we have according to our usual schedule, what is it that we have? We have group theory, I think. Group theory video is there from Herstein's Topics in Algebra, and along with that I think we have to solve group theory problems also from Galilean. So see you tomorrow with that. Until then, this is me, Lucifer, from a mathematical group. Have a nice night.